excited to be here after I haven't been here for 3 years due to Corona and stuff like that. I've been working with Bernard India for the past 5 years, and actually it's my baby because everyone is doing very standard irrigation things, and I'm getting luck to work with India and do things in a huge, big way, from a very old irrigation system to modernize them and to upgrade them to new irrigation, pressurized irrigation systems. And today I made a short agenda so it will be easy to follow. And of course, I rather that we will have a discussion rather than a lecture. So also if you want, I know at the end we will have Q&A, but if you want to barge in, feel free. I will be happy that we will share all the questions. So Lior did what Lior just presented, a short introduction of Bermad and why Bermad. We will talk really short about what is it, hydraulic control valve, okay, and how does it operate. But as Lior said, Bermad, the line of product, is not only hydraulic control valves. We are managing the flow of the water and air in the water system, so it's also air valves, flow meters, okay, and digital automation solutions. And we have the part of the accessories that we will talk about, which is the solenoids, the pilots, the brain of the hydraulic control valve, okay, that actually makes it a PRV or a pressure sustaining, okay, because the valve body is just a machine that we are operating and controlling. And we will talk about pressure reducing valve, which is the most common application. 70% of what we sell is PRV. So we will talk about standard PRV, and then about proportional PRV. And then we will talk about pressure management in a municipality, which is actually pressure reduction, but more sophisticated pressure reduction application. We want to share with you the idea of Bermad about pressure and flow control in the distribution lines in the upper network and also in the outlets in the OMS, and a surge protection solution when we come to talk about pumping stations, and reservoir applications, and my friends from Bermad India will also share their part about references and reservoir application. So let's start. Okay, so this is a very loaded slide, but it shows you what we do all over the globe, not just in India. If I try to put the cursor. Okay, so this is an OMS from package 21, I think, from the Orissa, from Orissa clusters. This is the outlet management system for 30-hectare chuck. Each valve is supplying here water for a 5-hectare, 2-hectare stack chuck, okay? Afterwards, it's being split to few farmers, okay? And you can see this valve also here, in this, if someone can hold it. So what Bermad idea of pressure reduction, okay? This is the valve itself, the valve body, and this is what we said, the control loop, the brain. This is pressure reducing pilot, and this is flow limiting pilot, okay? So we reduce the pressure before we go to the final irrigation method, if it's required, and we are limiting the flow. We will talk about limiting the flow a lot, but can someone just say in one sentence, why do we need to limit the flow in such systems? What do we want to protect? Just if you have any idea when we will need to use flow control feature. Think about the 80K hectare area providing water to 10,000 farmers.
Equal water distribution.
Equal water distribution. We don't want one farmer, two farmer, three farmer to take water on the expense of other farmers. And we don't want the farmers to create excessive consumption that will hurt the supply system. Okay? So this is very important feature when we talk about water association, when we talk about consortium in Europe, it's the same. In districts in the United States. So all over the world, because we are upgrading the irrigation systems, the networks, the small farmer, the private farmer doesn't have the money to do it, so I need a very big cooperative to take a lot of farmers and make sure that each one gets the flow he needs and the pressure he needs in order to grow his crop efficiently. Okay? And it's important to know that this flow control is hydraulically. So it's automatically, it's not dependent on communication, on energy, okay? It's done automatically and hydraulically, and we will talk about that. So I go back to the slide. You see here Bermad first product. This is the hydrometer, 900 series of Bermad. It is the first valve that Bermad invented. The name of Bermad is called after this product. Why Bermad? Beres in Hebrew is a valve, and a mad in Hebrew is a water meter. So this product is combining hydraulic control valve and a water meter in the same body. Okay, so it can give us the benefits of building a very compact irrigation control valve. And in India, in the past, we were a lot promoting this product, but as you can see, it's a metal product, and we are tending to promote more and more composite solution because of all the benefits that we said before, previously when we were talking. So actually, a composite solution that can replace it is this product here. You see 100 series valve combined with electromagnetic composite water meter. You see the electromagnetic metering that is wrote over there. And you can also see here, that we are replacing old hydrometers with new composite solution, or at least bypass this old product. What you see here is OMS, but it's from France. It's a cabinet. That's what the French people call it. Okay, and if I touch maybe it will run. Okay, it's the video of that they made of a demo cabinet in France. And you can see here, Bermad solution for the upper network in package 21, and I will talk about it as a case study of what we can offer. So let's talk about the big field. When we talk about pressure reduction, when is it needed? When do we need to reduce the pressure? When do we need to think about pressure reduction? If we are talking about, for example, here, we have a pumping station that need to provide sufficient pressure and flow in order to deliver the flow from the pumping station, from point A to point B, which is the most elevated, distant, critical point in the irrigation project. And it needs to give us sufficient pressure in order to overcome what? In order to overcome the head loss, the friction head loss along the line, okay? So what does it mean? That the pressure here in a zone which is very close to the pumping station. Here what we will have regarding the pressure, I need to design with a pump that it give me sufficient pressure in order to go here. But here I will have excessive pressure. I will not need this entire pressure. I don't need to design with a very high PN rating pipes or very high PN rating components. Check valves, gate valves, whatever it's in my system. So here I will need probably to install pressure reducing valve. Okay? So one point is distance from the pressure source. Okay, it's important. Another thing is topography. You know that as I go up, I lose pressure, and as I go downhill, I accumulate the pressure. And I need to think about pressure reduction and how to do it in a gravitational system, okay? And we will talk about that in more details as I continue. Here you see a different example that we have two reservoirs which are supplying, we supply water to this reservoir uphill. So we have a lower reservoir and an upper reservoir. And in order to make sure that this reservoir will get sufficient flow, we need to make an hydraulic prioritization. We need to apply some kind of a feature, okay, sustaining flow control, so to limit the flow into the first reservoir and to make sure that the upper reservoir will get sufficient water, okay? And we will talk about reservoir applications as well. So this is just in a nutshell, and I will elaborate more about distance from the pressure source, topography, and also variation in flow. Variation in consumption can also affect the pressure, and we will talk about this. So actually what I want to do is design a system with optimal pressure and flow. I have the designer office. They design according to a certain flow, according to a certain pressure, okay? And I want to apply these design boundaries, okay? So how do I need to do it? I need to actually have a device, a smart device, okay? Which we can call variable resistant device that adjusts its resistance, adjusts its KV, adjusts its degree of opening according to what's happening in the system, okay? Suddenly we have another pump adding. Suddenly we have some consumer closing their valves. We need to react automatically to these changes. And if we put a gate valve, for example, okay, in some point in the system, we put a gate valve and we adjust the degree of opening. And suddenly some consumer are closing and the pressure will rise, okay? Then this gate valve will not adjust automatically its degree of opening, okay? But hydraulic control valve, okay, will do it automatically, okay, and autonomically. So this is when we talk about regulating control valve, hydraulic regulating control valve. So it's actually a smart device that is is protecting the system and is balancing the pressure and flow and helping us to maintain the design boundaries, okay? Because, for example, we don't control the consumption. We don't control the farmers, but we need to react in order to protect our system, okay? Do you have any questions till now? This is just the basics. Okay. So, as I said, there are many different control valves. It can be a manual control valve. Sorry, a minute to jump back fast. Okay, manual control valve. Wait, I think it's okay. Motorized, which is, of course, need energy. Piston control valve, okay? And we have what Bermad is offering, hydraulic control valve, which is driven from the line, from the pressure in the line, okay? We are using the line pressure that is already there, because we pumped the water, in order to operate the valve, okay? So let's start to understand what is standard pressure reducing valve, which, as I said, is 70% of what we sell is pressure reducing valve, also in waterworks, okay? It's the most common application. So actually a pressure reducing valve is a small factory. And what it manufactures? It manufactures stable and constant downstream pressure, okay? So this downstream pressure, we calibrate the valve for a downstream pressure of 3 bar, and the valve will not allow the pressure to go above the setting. It will adjust its position in order to maintain a downstream pressure of 3 bar, okay? And it doesn't matter if there will be changes in the consumption, in the flow, or in the upstream pressure. As you can see in this graph, the upstream pressure is continuously changing. It's also affecting, okay? We can see also the flow is changing and affecting the pressure in the system, but the downstream pressure that we get is constant, but it's also adjustable. If we want to calibrate it to a lower pressure, or we want to calibrate it to a higher pressure, we can come and do it with our hands, okay? Manually, we can change it, and we will see when we talk about pressure management, we can also do it dynamically and automatically by using a controller. But this is more sophisticated stage, and we will talk about it. So why pressure reducing? It's actually what I said in the beginning, protecting the design parameters of the system, reducing pipeline PN rating and the components, and protecting them. And we will see now example of distance from the pressure source, elevation issues, topography, and flow variation, how it affects the pressure and how it makes us it requires a solution, it requires a solution to manage the pressure, to optimize the pressure. Okay, and this is the examples that I showed you before. So this is an example, this is an example for elevation variation. So you see that as I go uphill, okay, I lose pressure. Let's say I have an on-off pump with a constant pressure, supplying the constant pressure. So the valves which are close to the valves which are in the same elevation as the pumping more or less, they have more or less the supply pressure, but as we go up, okay, you can see that we are losing pressure, and as we go down, we are gaining pressure. So in this area, we are definitely need to think about pressure reduction. And in this area, we need to see that we are supplying here sufficient pressure, okay? So we will have the pressure that is required in this outlet, okay? So this is one of the considerations. When we talk about distance, like I said, from the pressure source, from the pumping station, okay? When we are close to the pumping station, more or less we get the what we got from the pump, okay? At the end of the day, now I kind of separate the distance, and I separate the topography, and I separate the flow. But you understand that when you are in a field, you have everything together. You have one zone close to the station, but going downhill, or going uphill, or flat. So we need to take all the combination of these 3 points together, okay? And this is what Lior said, that we in Bermad, we want to see when we want to be with you in this project from the start. This is how we can optimize the system and give the most cost-efficient solution. So we want to see the map with all the data, and we want to be with you from the pre-sale, okay, when we start to design this project. And if we talk about flow variations, let's say now all these 5 consumers are consuming water, all these 5 farmers, okay, all these 5 plots, okay, whatever we want to say, and then the pressure is 4 bar, okay, in the system, and at the outlet we are reducing to 2 bar, and now few consumers are closing their, stopping the irrigation. Okay? Just a second. Okay, so now these consumers are closing the irrigation. What will happen to the pressure in the system? It will rise. Okay? I'm pumping the same amount of water, but only part of it is going out. So the pressure is rising. Okay? It's like an Indian road that everyone goes in. If we block one lane, then the pressure will rise, right? And I was traveling yesterday from Mumbai to Pune. It was very, very pressurized road. So the pressure is rising, and now the reduction ratio that this valve need to handle is bigger, okay? But again, you need to make sure that you understand that there is no separation really in the field between the elevation, the distance, and the flow. It's all happening together, so we need to consider all of these parameters together when we design. Okay. So again, pressure reduction. Usually when we talk about pressure reducing, we don't talk about one product. Anyhow, in Bermad we sell solution, and in India it's even more strongly. We don't sell only products, so we talk about actually pressure reducing station, okay? And what do I mean station? I mean that we need an isolation valve, okay, for maintenance issues. I need a strainer or a stone trap, okay? In order to what? To protect the valve seat, okay? And to protect the control loop. Control loop is usually 8mm control loop. You can see it here. So we don't want debris and the particles, okay, to go and to damage the valve seat or the control loop. Nevertheless, in our control loop, we are using an inline filter, okay, to protect the control loop. I can show you later. I have in my bag an inline filter, so you can see it. And then pressure reducing valve, followed by a quick relief valve, okay? Why a quick relief valve? Why we always recommend to install downstream to a pressure reducing valve a quick relief valve? Can anyone imagine? First, we want to have an indication if there is a malfunction in this valve, okay? Even though Bermad valve never has a malfunction, but in the remote chance that something will went wrong here, okay? Maybe someone even did not calibrate it correctly, the pressure reducing valve. We want to have an indication that the quick relief will start to relieve a lot the pressure, okay? And the second thing is, until a pressure reducing valve will react, it will take some time, okay? For double chamber, it will be very fast. For single chamber, it will take a little bit longer time to adjust the position for the new flow. Because as I said, it's adjusting its degree of opening all the time, according to the system condition. So until this pressure reducing valve will react and adjust its position, and again, reduce to the setting, the quick relief will protect the downstream pressure. Okay, it will relieve the excessive pressure for a few seconds until this valve will react. Okay, so always a quick relief at a downstream of a pressure reducing valve, and again, an isolation valve. Don't be shy. Do you have any questions? Okay, we continue? Yes. Okay, so as I said, we can talk about, when we looked on the map, we can talk about different pressure zones, right? We have some area close to the pumping station who gets high pressure, and a more distant and elevated place with area that is gaining less pressure as we go far away from the pumping station and uphill. But we can create different pressure zones even on one irrigation control head. A very small and limited area can have few pressure zones. We actually have few pressure zones when we apply pressure reducing. We have the blue zone, which is high pressure coming from the supply to the irrigation control head. We have now pressure reduction, and at the downstream of pressure reduction, what do we have? We just talked about it. What do we install at the downstream of a pressure reduction?
Quick relief.
Quick relief. Why we are reducing the pressure here? Maybe because the PN rating of the filters requires us to reduce the pressure. And then we have two hydrometers that are delivering the water to the plots, okay? And let's imagine that this plot here, close to me, is delivering water to downhill. So I need to reduce the pressure again, and I create another pressure zone, okay? And the other plot is going flat, okay? So I don't need to reduce the pressure. So in a very small irrigation control head, very limited area, I already created 3 pressure zones, okay? About this, I want to make it short about the control types. So actually we have 2 types of control loop. We have the two-way control loop, which is more applied in waterworks, and we have the 3-way control loop that we apply very commonly in irrigation, okay? The most important thing that you can identify is when you have a valve with a vent to the atmosphere. You can show Pushka. When you have vent to the atmosphere, 99% it's a 3-way control loop, okay? And when the control loop is closed, you see, okay? It's from the upstream of the valve to the downstream, and you don't have any open tube to the atmosphere, it's a 2-way control. Okay? And I can say that the 2-way control is very simple in structure, okay? It has an inlet branch at the upstream of the valve. By the way, Bermad is saying upstream P1, downstream P2. This is what we use in our language. And when we talk about a valve control chamber, okay? The pressure in the valve control chamber, we call it P3, okay? And actually, what the control loop is doing, it's controlling the pressure inside of the control chamber of the valve, okay? So if we have a lot of pressure in the control chamber, if we are pressurizing the control chamber, what are we doing? Are we closing the valve or are we opening the valve? If we put water inside here, what are we doing? We are increasing the pressure in the control chamber and we are pushing the valve toward closure, okay? And when we are venting the water from the control chamber and we are decreasing the pressure, we open the valve. And this is how actually we are controlling the degree of opening of the valve. So the control loop helps us to control the pressure in the control chamber, and the valve is then changing its degree of opening where? In the main line, affecting our system, okay? So let's talk a little bit about the control loop. The control loop is usually using control accessories like pilots, solenoids, hydraulic relays, etc., etc. And you can see here that this is a very simple control loop. We have the inlet branch to the control loop, and we have here a restriction, okay? Because we want to restrict the flow going into the valve, okay? And to restrict the closing speed, okay? We know that in systems, if we talk about surge, we don't want valves that are closing very fast, okay? So we need to restrict the closing, and also there is an issue between the ratio of the restriction to the water path that we are seeing here, okay? And this is a pilot, okay? This is a control accessory called the pilot, okay? And it's dynamically changing the water path here, okay? If I'm talking about things that you already know, just let me know so I continue. Okay, Amay and Farsad, Amay, should I continue or we don't need to elaborate on this?
You can just show them like basic show like how the ball operates. Example like what is upper chamber and what is down, and like how the ball opens and closes.
Okay,
you show three-way loop.
Yes, I think I showed the movie. I will show
Animation.
the movie of the three-way. Okay, this is a three-way control loop. Okay, it's actually done now manually, but in the pilot we are doing it automatically. So let's assume this is the pilot, okay? And here we are connecting the pilot to the upstream, the line pressure actually. And here we are connecting the pilot to the control chamber, okay? And this is the vent to the atmosphere. And we have here some kind of a shaft, okay? With the ball, okay? So now let's, Vidit, can you press on the video? So now let's see when we pull, what happens, okay? No, on the, yeah. So when we pull, what happens? Water flows from the upstream to the control chamber, pushing the valve down, the diaphragm, and towards the closure, the seat, closing the valve, okay? And when we push, okay, water are venting from the control chamber to the atmosphere, and the valve is opening, okay? Now the valve is open. Once we are reducing the pressure in the control chamber, the valve is opening. So this is very fast about three-way control loop, and the pilot is doing it automatically. And the pilot is reacting, it's connected. For example, if it's a pressure reducing valve, the pilot is connected below the diaphragm of the pilot. Go here. You see, this is the pilot. It has a diaphragm, okay? Above the diaphragm, we have the calibration spring, and we set the calibration.
You can see here there is a screw. So we can set on a test bench, whatever test pressure or downstream pressure we need.
All the valves from Bermat are preset, are pre-calibrated, and Bermat test bench on water, on the hydraulic test bench, according to the requirement of the project. But nevertheless, you can change it in the field, of course, okay? So above the diaphragm of the pilot, we have the spring and the force of the spring, and below, what we are sensing, it's a pressure-reducing pilot. So you see the sensing tube here? We are sensing the downstream. We want to control the downstream pressure, and we sense the downstream pressure, okay? So if the downstream pressure will rise, it will increase the force below the diaphragm, okay? And if it will rise above the setting, it will beat the force of the spring, okay? And this entire shaft and ball will go up, okay? And water will go from the upstream, from the line pressure to the control chamber, and will close the valve in order to reduce the pressure. So all the time, the pilot is changing the water path and reacting to changes of the downstream pressure, and this, as a result, the valve is changing position in the line, okay? So this is what I mean when I say we all the time react hydraulically, autonomically. We don't need electricity, we don't need energy, okay? We don't need communication, okay? Even though we all like to be connected, this is done unconnected. And it's quite amazing.
Sorry, can I ask a question?
Yes.
So a lot of our clients are a bit more concerned with regards to the maintenance that is needed for these valves.
Yes.
So my question essentially is, in your experience, in Burmai's experience, the amount of valve installations that you've put in all over the world, without any electricity maintenance, without any control or electricity, with probably some minimum or prescribed timely maintenance, where do you see failures happening, or what do we need to worry about, or how can we convince our clients that these are robust solutions for say 15 to 30 years or whatever the valve life is, 15 years?
Okay, I will answer that, and Pushkar and Bhagwan that are actually in the field can also give you the input. First of all, we have a recommendation of changing elastomer kits every 5 or 7 years, and this is written in our IOM, so this is one maintenance issue that maybe we should take care of, but it's like every 7 years, 5 years in the field operating, okay? It also depends how frequent the valve is working, yeah? And also the issue of the inline filter is self-flushed, okay? But still maybe sometimes when we talk about very loaded water, we might need to flush the filter in the control loop. We can bring the filter, but Pushkar, Bhagwan, you can elaborate more about maintenance issues.
The main thing is the control chamber is the diaphragm, which will be partition.
Yeah, the elastomer kit, what Sarit was saying is nothing but the diaphragm, which will be dividing partition for the control chamber. So what happens when it is continuously running 5-6 years, some sand particles may come and deposit there. So what we recommend that in 5 to 6 years, you can once see if the valve is still running good, no issues, or you may need to clean it or replace this diaphragm. And another advantage in Burmah valve, you can see the here top portion. The all bolts are here, so you can remove the entire stem assembly from the top. You don't need to remove the valve from the main pipeline itself. So you can take entire system out, you can examine whether any damage is really happening, and then you can replace. So it will really save your maintenance time on huge scale. Even for the higher metal valves also, we can remove this part from the top portion. So maintenance is really easy, and we can say the life of the valves is really good.
So, just a follow-up question. In the same installation, we put a pressure release valve as well, mostly, just to check whether the pressure reducing valve is working well. Okay. Now, many a times this is in a chamber, and the chamber is not properly drained. Okay. So, what happens to the valve if the chamber is also flooded? Does the valve stop working, or does it continue to work as?
No. What she is saying, if that water accumulates in the chamber, what will happen to the valve?
Again, the valve will continue to operate, but when we have a metal valve with water, it can cause us issues of, I don't know, corrosion, things like that. We can think about maybe taking a pipe from the quick relief to somewhere, but it will not harm the functionality of the valve. Nevertheless, it might harm the accessories from metal and stuff like that. Or maybe you've seen things like that, and you can elaborate as well. When you have a pit and the quick relief is pulling water to the pit and it's flooded with water, how can it harm the valves and the operation?
It's not. If I understood correctly the question, it's not harming the valve, it's just not a right way of a system to work. That the quick relief, or the quick relief should be only for emergency cases.
Yes.
So if it works all the time, it means that you don't operate the system in the correct way. You spend water. No, it can work, but it's like you are driving with the handbrakes half pushed, so the car still moves, but you know it's not the right way to do it. That's all.
Okay, we continue. Luckily we have Farsad with a question. Okay. So this was standard pressure reducing. Now we will talk about a simple pressure reducing, what we call proportional PRV, okay? Or Okay, in Hebrew we say מקטין יחסי, but we don't have it in English. So actually, if the standard pressure reducing was manufacturing a constant adjustable downstream pressure, this proportional PRV is manufacturing a constant ratio between P1 and P2, okay? Regardless of changes in flow and upstream pressure, always the ratio between the upstream pressure and the downstream pressure will remain constant. So if we look on this graph, on this specific example, okay, we see that when the pressure is 7.5 bar, the P2, the downstream pressure, okay, is 2.5. The ratio between the upstream and the downstream is 2.5. Now the pressure, the upstream pressure, supply pressure is decreased to 5 bar, and the downstream pressure that we are now getting after the valve, okay, is 2 bar. So still the ratio is maintained. So a proportional PRV is producing us a constant ratio. It's good when we are along the line and there is no significant for a specific set point, okay? And I will show an examples, but when I say it's very simple, why do I say that? But it's because it's without any control accessories, okay? It's without a pilot, without a restriction, without a filter even, without an inline filter. Very simply, we are connecting the upper control chamber, the upper control chamber of the valve to the downstream by using a tube, a control tube. That's it. The only important thing that this can apply only on double chamber configuration. Yes?
Yes, and like, I just wanted to say this question because this is this is like the solution at the moment which we wanted to use in our Odisha project in India. So I just wanted to see like department or the other engineers on site client are not having trust because they feel about it will have high maintenance. What if it fails? Like the queries what they have is what if it fails. So according to you, what are the chances of this valves to fail? And if fail or not operate with this installation, if it fails, what will happen? Because I'm sure the cost of valve is not much, but the downstream pipeline is an example covering like 50 to 60 villages example. So the impact on this is what the risk they have is okay. It may be a solution in the market or it may be the solution which you give, but if it fails, it will destroy my entire villages downstream or it will destroy the pipeline downstream. So what do you think, or what should be the answer to it? What do you think?
First, I want to say that the chances for fail are very, very negligible because we have nothing to fail here, really. We don't have a control loop. We don't have anything that can fail. But usually what we are applying is few proportional PRV at downhill, and we will see it one after the other, okay, in theory, okay. This causes a very stable operation because they're not overshooting, okay. It's very stable operation. It doesn't cause oscillation and hunting in the system. And regarding maintenance, it's very easy to maintain. It doesn't need any maintenance because we don't have any accessories. So the real issue that Bermad is standing behind and providing is to allocate correctly the valves along the gravitational line and taking into consideration also approachability to the area of the valve and taking into consideration how many units we put along the line and the different scenarios of dynamic scenarios and static scenarios. Okay, when, for example, at the end of the downhill we have a valve and now it's closed, then now this valve will need to reduce pressure, higher pressure, because now we are talking about only the elevation difference and not taking into account the head loss. Okay? So allocating this valve correctly is important. But really, I hear more and more projects in China that they have very long gravitational lines and they install proportional pressure reducing valve, and they work perfectly. So, Amay, if you want, I can...
Sorry?
Yes.
Maybe I think that I understood what you're asking. The proportional pressure reducing valve cannot replace the regular PRV for protecting the pipes. In the end, you must have PRV. Just as I said, just the way to reduce from very high pressure to low pressure. So in the middle you put it, but in the end you need a regular PRV to set the pressure to a fixed pressure. This is sorry.
Okay. But you know, Amay, I can also, because we are globally spread, we hear a lot of troubles from the clients, if there are any, and actually about PD, we hardly hear. It's a very stable and reliable solution. Okay? Quick relief is also important at the end of a gravitational line to protect, okay? If we talk about a gravitational line. I don't want to give it a lot of time because the equation might be a bit tiring, but if you look on this valve, when it's not connected to the downstream, when the control chamber is actually not pressurized, it's open to the atmosphere, and pressure is coming from the supply, okay, here. It's pushing the closure, and I have some pressure here at the downstream because water started to flow, and what will happen now to the valve? Most likely, it will start to open because on the same area, I have two forces, and this force of the P2 is lower, okay? So the valve probably open, and if I connect the control tube, as I said, from the upper control chamber to the downstream, okay? This valve, what will happen to it? It will start to close, okay? Because now I'm applying another force of closure on the diaphragm. You see? This is the upper control chamber, this is the down control chamber vented to the atmosphere. This is the way double chamber looks like, okay? Double chamber valve. And now the closing forces are bigger toward the closure because it's acting on this area of the diaphragm, which is, in this explanation, twice the area of the closure, okay? So if you look on the equation that I will not get into it, you will see that this valve will start to close until when? Until we will get into equilibrium between the closing forces and the opening forces, okay? And from this equation, we can actually take out the ratio between the upstream and the downstream, which the valve gives us. And if you look on Bermad catalog, for each double chamber series, which is 700 and also 100, we also have composite double chamber, which I think are unique in the market. No one else has the double chamber composite product. Then you will see we have a table of ratios per each diameter in each series. What is the reduction ratio specified for this valve, okay? And if we get into more details, you will see that we have a flat cylinder, flat closure compared to V-port. V-port is this device, okay? We use it many times when we want to make sure that the operation of the valve is very, very stable in low flows, okay? And when we put this V-port, what happens? It pushes a little bit the diaphragm up. So the effective area of the diaphragm is now bigger. And this affects a little bit the ratio of reduction. So you see that the ratio of reduction is bigger with the V-port compared to flat. Just remember that when you see it, it might be too detailed now.
Sorry.
Yes.
What is the material of that diaphragm?
What?
Material of diaphragm.
The material. It's I think NR, NBR, NBR, MOC.
And we have optional as EPDM also. So
What is its like?
EPDM for waterworks if we need, right? For drinking water and
different material.
Nitrile rubber. Nitrile rubber.
Like,
life means, as they say that
because what I can see, the most important part is that diaphragm.
Yeah.
So what is its life in consideration operation and maintenance?
Before you answer Pushtam, I just want to say one important thing about the diaphragm. You see that in a double chamber, the diaphragm is not exposed to the downstream pressure. It's not exposed to the flow. You see there is the low control chamber, which is vented to the atmosphere. So this diaphragm is actually protected. It's protected from the flow, and if you have chemicals in the flow or whatever, and also mechanically protected because you see that we have the separation partition. You see this gray part, which is metal. So it's actually also mechanically protecting it from particles in the water. This is important in double chamber. Yeah.
You understood where is the diaphragm? That- So this is the diaphragm, okay, and this is your seat. Okay, so this is what is we tell in Burma that these two are different parts in Burma valve. Even it is in a plastic valves, also same thing, single chamber or in the metal valves. So your whatever extreme pressures happens in your main line. When you close the valve, you are paid to empty. There is no pressure in downstream line. Full pressure in P1. So seat is which is subjected to extreme pressure barrier conditions in longer times. So that is why Burma designed that we need to differentiate diaphragm separate and seat separate. So it considerably improves the life of diaphragm. If you go other, there are many competitors in the market. They use this diaphragm as a single closure, closing the seat always, also using for the pressure management. So that creates unbalanced diaphragm. You have huge pressure on P1 sometimes, P2 is empty, and then diaphragm life will considerably drop. But that is not the case in what products which Burma is offering. And the life generally goes what we are also installed earlier. We used to do projects along with other dealers like Netafame. Almost valves are installed for almost 5 to 10 years. So still there are no replacement, or the client has not asking any replacements.
What is the exact pressure reduction? In the previous slide I saw it's 2.5 and here
It's just an example. It's just for the simplifying the example. Each valve, each diameter in each series, 700 or 100, you will see in the catalog the exact ratio, and it depends, of course, on the ratio between the areas of the diaphragm and the seat, okay? And the effective area of the diaphragm, like I said, with V-port, without V-port, okay? So you can have it inside of the catalog to know what downstream pressure you will get.
Yeah, but PD we can go to this formula, I think.
Yeah, it's,
1:3.
if you look on the catalog, you see that the ratio is varying between 2.5 to 2.7, something like that, okay, depending on the diameter, okay? I didn't put the table here, but you can show in the catalog later. Okay, so as I said, no pilot, no accessories, we don't need to calibrate, we are less in a chance of clogging the accessories because no accessories, no filter, and immediate reaction. Why? Because first of all, it's a double chamber, and I probably will not have a lot of time to talk about this today, but you see when a double chamber is open, on the closure area, more or less the forces are equal. But when we get the command to close from above on the diaphragm, it's very strong. It has nothing to resist it, okay? So this is why double chamber will react immediately when it gets command to regulate or to close, okay? But at the end of the closure, it will slow down. So it's force, it's a lot of force to close, it will react fast, but it will not slam, and it will not create a secondary stage, okay? Which happens in single chamber. But we can restrain it as well by adding accessories in the control loop, okay? Okay. So if we talk about, again, about pressure reducing station, okay, not just the product, when we have a big reduction ratio, okay, and usually we go for a reduction ratio or typical reduction ratio of 3 to 1. We don't want to reduce more than that because then the valve will work under high operating load, okay, maybe get into cavitation conditions, and it will reduce the lifespan of the valve. So what we do when we have high reduction ratio, when we need to reduce from 10 to 2, okay, we will use 2 valves, okay? One valve will be the proportional pressure reducing, and it will reduce the pressure, let's say from 10, if we divide it to 2, it will reduce to 5, okay? And now this valve, the standard PRB, will only reduce from 5 to 2, okay? So the load on this valve will be minimized. So what do we do here? We divide the load. Ladies, divide the load with your husbands. It's very important, otherwise we crash. So this concept is good for life, okay? Dividing the load. You don't need to take everything on yourself. Okay, we continue. So let's talk about application down here, okay? Gravitational lines. We have a reservoir, okay, delivering water gravitationally to a lower reservoir, okay? Lower topographical zone. We have demands on the way, we have consumers on the way, and usually what we do in India, and what we used to do also in Israel for many years back, is installing pressure braking tanks, okay, along the line. Pushkar, can you push? I want to see what's next. Okay, so what happens when we install a pressure braking tank? It breaks the pressure completely. We're starting from 0 again, okay? Where I put this reservoir, usually they are small reservoirs, okay? I start from 0 to gain the pressure again as I go down here. So first of all, it's very safe because I break the pressure completely, but I also lose energy and pressure that I have that I can use, okay? And I need to have space, first of all, available. I need to build infrastructure for this reservoir. I need to take into account what? Level control valve. Okay, I don't want this reservoir to overflow. Okay? And this level control valve will work very hard. Why? Because if we are now at 10 bar pressure, and it's breaking and it's pouring the water, the level control valve is pouring the water to the reservoir to very low pressure, maybe to the atmosphere. If it's spilling top or 3-4 meters, it has a very high load on this valve. So we will put another proportional before it. So we are talking already about 2 valves, okay? So we need to take into consideration all of these benefits and other things that are less cost effective, okay? And the other solution, the alternative solution, like Amay said that we think about in Orissa, is installing proportional PRVs in series, okay? In order to reduce the pressure along the line, okay? And according to that, we can design our PN rating of the pipes, and we save space, we save maintenance on this reservoir. If we talk about waterworks, we also need to fresh the water. We need to take care for contamination, okay? So it's much more cost effective than the reservoirs, okay? And the only thing is that we are still having pressure, okay, which is good for the irrigation or for the consumer to have the pressure, but it makes a maize client worry what will happen if we fail, okay? Okay, let's continue. Okay, so again, no level control valves are needed when we talk about PD. We have no zero pressure at the downstream. We can use the pressure that we have in the line. Immediate response, like I said, maintenance-free, no pilots, no restriction, no filters, no issue of contamination, and cost-efficient infrastructure. We need if you press another press, Pushkar. No, back. Another one back. We still need some structure for the PD, of course, but it's not like a concrete slab and space for the reservoir oil. We need the valve to be approachable, okay, for maintenance. And all other things that we need to consider for both options is the issue of air valve and pressure relief, like I said, and of course a strainer, okay, for both reservoirs and proportional pressure reduction. And if we need backup, because we want to maintain one valve and we still want to supply the water, we need to have a backup system. So you will see that Bermad have a lot of tools, designing tools, that were created and invented by Bermad, and one of them is this Excel sheet. Some of you know it very well, to allocate and to size the correct proportional pressure reducing valve along the gravitational line, okay? So all the application of proportional pressure reducing beside gravitational. First of all, splitting the load on two valves when we have very high reduction ratio. We talked about it. We can see here an application that is actually like a hydraulic VFD, the circulation valve, okay? When we have an on-off pump, for example, two on-off pumps, okay, supply each 50 cubic per hour, but we have a changing demand. Let's say now the demand is 70, okay, cubic per hour. So what will we do with the extra, okay, 30 cubic per hour? We don't have a VFD, okay, on the pumps, it's on-off. So we need to circulate the delta between the maximum demand, which is 100 cubic per hour, to the current demand, which is 70 cubic per hour. So we actually circulate this water back to the water source. So it's kind of like hydraulic VFD. We can also use it as a backup to an electrical VFD, just if the communication fails, okay? But this valve will always sense the discharge pressure of the pump. So it will sense a very high pressure, let's say 7 bar, okay, 8 bars. And it will discharge back to the water source, to very low pressure, 0, 3, 4 meters, okay? So it will work very hard. So what do? We add a proportional pressure reduction to help it to divide the load on two valves. And same goes for the reservoir filling, the level control valve that I already mentioned when we talked about reservoir along the gravitational lines, okay? Why to minimize the load? Why to minimize the load? Because we're afraid that the valve will work under high operating load and will get into cavitation condition. We don't want the pressure in the vena contracta. The vena contracta is a term for the very close to the seat of the valve. When the valve is regulating, it's very close to the seat, okay? And there could be situation in a certain flow velocity, okay? Depends on the temperature and many things, that the pressure will drop below the vapor pressure. And what will happen? Bubbles will occur, the water will transfer from liquid to gas, and these bubbles, after the pressure will recover, when we move from the seat of the valve, they will harm the body of the valve. They will explode like jets in a very high velocity, and they will harm the valve. So this is why we want to split the load on two valves, okay? And we can talk a lot about cavitation phenomenon. It's a big.
Can you move 2 slides back, please?
Yes.
But the circulation system is the same it's the same mechanism that we use in a pressure or in a surge solution, or maybe is this the same or the same principle of a solution that we use in a surge situation as well, where we have additional pressure going into the system and then we discharge some flow back?
This is a pressure sustained pilot, okay? Yes, it senses the rise in pressure due to the fact that the demand is now reduced. A surge protection SAV, actually what makes it open is the reduce of pressure. Due to the fact that the water column is now going up and the vacuum conditions, the pressure is dropping and we might reach vacuum condition, the pressure reducing pilot is opening the valve. So it's different
application.
Different application, different pilots are doing this, okay? Yes. Downhill system?
Last PRV.
Yes. Actually, this is not a PRV. Probably it will be flow control or flow and level control, I would say, because it will make sure that the reservoir will not flood, and it will also control the flow that is filling the reservoir, because we have a lot of energy going down, and we don't want to fill the reservoir too fast, okay?
If there is no demand at last wall, this wall is closed.
Yes.
That time static head is also controlled by this one.
Yes. The proportional pressure reducing is also reducing more or less in the same ratio in static conditions as well, okay? It could be 2 meters above the ratio, okay? So if we do 2.5, okay, it will be a little bit more in the value, but it will still seal, drip tight to reduce the pressure, okay, before in the static conditions, okay?
Okay. Thank you.
This is a question that a lot of clients ask, okay? What happens with the proportional PRV at static conditions?
What is the limit for high reduction ratio?
What?
Is there a limit setting for high reduction ratio? It is going from this value then?
Usually we say typically 3:1 reduction ratio, but it also depends on how much time, how frequent the valve is operating, for how many hours a day, okay? So it also we take this into consideration, but 3:1 is typical.
Sid, can I just wanted to see, just to check with him, because we do our system design. Can I assume or can I consider that in PDB, in proportional reducing, it can go to 3, 1:3, and if we are having high reduction ratio, if we are having 2 valves, can we have 1:2 in your downstream valve and 1:3 in upstream valve, which will have an effective ratio of 1:5 if we use 2 valves back to back.
So you need to
sorry. Example. I'll just explain that if there is a pressure of 10 bars, can I use proportional reducing to reduce it, say from 10 to 3.5? Example, with the proportional reducing, and from 3.5 to say about 2 or 1.5. So that effectively I'm coming from 10 bar to 1 bar or 2 bar.
Yes, of course.
That's what, yeah.
This is the fact that we are using 2 valves allows us to have a at the end, the bigger reduction ratio from 10 to 1.5, like you said.
Yeah, so it means what you said 3 to 1 is for one valve.
One valve.
Yeah.
Sorry if it wasn't clear. One valve. I mean that if you will approach me and as an application engineer and will say we have a condition where we need to reduce the pressure from 8 to 4, which is a ratio of 2, I will say, okay, probably we will use one valve, no need for more. But if you will say from 8 to 1, immediately I need to think about dividing the load on 2 valves, okay? This is the, I hope it's clear.
Sorry, one more question.
Yes.
We are reducing the pressure from 10 to 1.
Yes.
This is abrupt change. What is the effect on the system, complete system?
Okay, what do you mean by that? That the PN rating of the pipes that you can use is lower, okay? The components should be with a lower PN rating. I just, what do you mean? Where is the direction that you're taking?
What if it fails? In that case, what will happen?
If it, first of all, you always put a quick release valve when at the downstream of the pressure reducing, and you can also put another quick relief valve between the PD and the PRV. I show it here. Okay, you see here, we even were holier than the Pope. The Pope in Rome, you know, is very holy. So here, it's a very holy system. We put a quick relief also after the PD. So if this doesn't seal drip tight, we have an indication from the quick relief and it's protecting the system. But if you don't want to put money on the quick relief, we can even install here just a pilot that will give us the indication that something is not operating good here. Definitely, you need to put here a quick relief. Okay? So, when we go to colossal cases, nothing happens to the system, okay? We have the quick relief to react and give us the indication, okay?